And welcome back to whatever week this is, Super Sleuth Edition. So today we'll review the basics of ordinary least squares, and really what we're going to focus on today are the assumptions of ordinary least squares. Remember, all statistical techniques, all methods, all tests that you'll ever see rest on some assumptions, and ordinary least squares is no different, so we'll talk about what those are and look at the consequences of these assumptions. Announcements, new announcements. So coursework 1 deadline's postponed. I made a Moodle announcement about this. It's now due April 27th. It's now worth 100% of the module mark instead of 50. So to be clear, there is no coursework 2 anymore. It's posted. You all are working on it. Great. So for the rest of the week, for the rest of time, no, for the rest of this term, the issue is coursework 2, I had planned coursework 2 to be part of the module. Now it's not. So what that means is that the scheduled drop-in session first week after break is useless because there is no coursework for you to be working on. So I'll come up with some other super fun, amazing activity for us to do then. All right, where are we at? Where we're at is the world of linear regression. We've assumed there's a relationship, indeed a linear relationship, between some variables that we've identified as explanatory variables. These are called independent variables, and a single dependent variable, usually abbreviated y, which is the phenomena to be explained. So here's what that looks like. If we were interested in what accounts for wage, we might ask, does education matter for wage? And the linear regression assumption is that there is some linear relationship between education and annual wage. And then our inference task is to then just estimate that line. So remember what a line is. A line is just two things. It's a slope and it's an intercept. You give me a slope and intercept, congratulations, you've actually given me this here blue line, and vice versa. So remember the setting of estimation. First, there is some truth out there. There's this conceptual tool that we developed last term called a population. This is the set of things you want to learn about, or the entities you want to generalize to. And there is some truth. It's out there. I don't know what it is, but it's fixed. So truly, there are some numbers, beta naught, beta 1, and sigma squared, such that truly person I's wage is determined in the population by whatever this population parameter is, plus whatever this population parameter is, times how much education person I got, plus everything else that matters for person I's wage that isn't their income. So this truth exists. It is out there, it's in the population, but we don't know it. In fact, we can't know it. But that's okay, we can estimate it. And this leads us to the regression equation. So if the population equation is thusly, we can estimate beta naught, beta 1, and actually we can even estimate these errors on the basis of what we've actually observed, on the basis of the sample values of our variable x and our variable y. So remember, estimates get hats. Sometimes I'll call an estimate of beta naught as b naught, and an estimate of beta 1 as b1. So then, once we've done estimation, once we've performed linear regression, we get the regression equation. We get an estimate, an estimated intercept, an estimated slope, and as a result, we get a way of making predictions. For a given value of x, for a given level of education, we can predict what person I's income would be. So this is called the linear model, or the classical linear model, or classical linear regression model. Great. So this is just review. We've got a dependent variable, we've got independent variables. We're going to start with only one predictor. Okay, so ordinary least squares is one way of coming up with those estimates. What are the assumptions underlying that estimation? So ordinary least squares as an estimator. So we can use ordinary least squares to estimate the linear model. That is to say, it gives us a way of estimating parameters, beta 1, beta 2, beta naught. How does ordinary least squares do this? It does it by minimizing the sum of the squared errors. Now, I should say that there's other ways of doing estimation. There's generalized least squares, maximum likelihood methods, Bayesian methods, and whatnot. So this is a way of coming up with guesses, with estimates. So all estimators and hypothesis tests rely on assumptions. For example, you usually maintain that observations are independent of one another. So what are the assumptions of ordinary least squares? Well, there's two categories of assumptions in statistics. The first of which are model-based assumptions. So these are assumptions about the population. So we saw some of these last term and this term. No. Yeah, we saw some of these last term and this term. So, for example, some tests, like the single sample t-test, makes assumptions about how a variable is distributed in the population. For example, the single sample t-test assumes that the population distribution is normal. So these are called model-based assumptions, and they're distributional assumptions, assumptions about how things are distributed truly. There's other kinds of assumptions called design-based assumptions, and basically these assumptions are, the way I like to think about it is they're assumptions about how it is that we got to see what we saw. So they're assumptions about how a sample was gathered. For example, was the sample collected via a simple random sample? Was it stratified? So on and so forth. Ordinary least squares relies on both kinds of these assumptions. So here they are. Here are the assumptions of ordinary least squares. They are linearity, no indigeneity, normality, and homoskedasticity, a fun word to say, only if you haven't had too many beers. No autocorrelation, no multilinearity. So don't worry, we're going to cache each and every one of these out one at a time. So let's start with linearity. So ordinary least squares assumes that the relationship between these explanatory variables x and the dependent variable y is a linear one. So what does that mean? That's not actually as limiting as you might think. The linearity here isn't very restrictive. Really, all it says is that these coefficients, these betas, aren't squared or cubed or anything like that. For example, here is a linear relationship between y and x. Here's x, here's y, and this here line represents the linear relationship between x and y. Here is a linear relationship, not between y and x, but between y and x squared. So in gold, I've plotted x, and the dark line here represents the relationship between x squared and y. So this is still linear. This is still linear in the parameters. All I've done is I've just included a new independent variable called x squared. And sure enough, the relationship between y and x squared is still a linear one, namely given by this here line. And we can do other fancy stuff. So really all this linearity assumption says is that these betas aren't squared or cubed or whatever. So that's not super restrictive. The second assumption is restrictive and super important, and it's called no indigeneity. So what this says in words is that the errors, that all those things that go into determining person I's wage that aren't their education, are independent of the included variables, or independent of education. So it's perfectly fine to say, look, we haven't included all the variables that determine somebody's wage. We haven't included parents' SES and charisma and the color of the tie the candidate wore when interviewing or whatever. It's fine to omit variables that explain why, as long as they're completely unrelated, as long as those factors are completely unrelated with the included variables. Okay, so how could this come about happening? So how could this come about happening? This could come about happening if these errors are correlated with the included independent variables. So in our running example, if everything else that helps determine wage, like let's call it ability or hard work, is correlated with what we have included with education. If that's the case, whoops, then we're in trouble for inference. So how could this come about? How could you have a situation like this? Well, one such way is via omitted variables. So imagine that there's a variable called z, and that z explains the dependent variable y. So imagine that ability helps predict wage. And further imagine that ability is in fact correlated with the included variable. So imagine that ability is correlated with education. Probably not a ridiculous thing to imagine, at least. Now, if we did not include ability, if Z was not included in the regression, this could come about by a number of ways. Maybe we just don't have a way of measuring ability. Maybe we do, and we as the researcher just haven't included it. So if Z belongs in the regression but is not included, well then what happens? Well then, what have we got? We've got Z is not included in the regression, so that means it's captured in that error term. It appears as everything else that affects wage that isn't it appears as everything else that affects income that isn't education. So it's in that epsilon term. But we've just said that this Z is, that ability is correlated with education. So now, what's happened, because we didn't include Z in the regression, everything that we didn't explain goes into that error, so actually this error becomes correlated with the things that we've included. Whoops. So that is an example of endogeneity that comes about by virtue of not including essentially all the variables that we should, by omitting a variable that, in quote, belongs in the regression. So what's a way to safeguard against this would be to include the variables that belong. Now, how do you know if that's happened or not? Well, you never can fully know that. There's some, so theory is one guide, is a principled guide. Later on, we'll see there's some statistical kinds of tricks maybe we can play. But at the end of the day, endogeneity is a real problem. It's a real problem for researchers that we really need to take seriously. Let's take a break.